Hi there. In our previous class, we looked at conservation of momentum. We saw that if we had a system with a bunch of objects in there moving in various directions, and if they were to collide with each other, um, the total momentum of the system would remain the same during any time of this process. So let's say if you added up all the momentas and you found out that it was 3 kgms was the net momentum in that direction, then even after they collide and do whatever amongst themselves, you take a snapshot later, and again, if you were to add up all the momentas, you would see that it will still be 3 kgms in that same direction. And we saw how we looked at different types of collisions and managed to figure out what the aftermath would be, or during any time of the process. Now, what happens if there is an external force? Well, we are going to first define this term called impulse. An impulse is a force applied over a period of time. Anytime you apply a force, it's not just for no time, it's for a certain period of time. And sometimes the force is constant and sometimes it is not. So impulse is basically a force applied over a period of time. And we take the product of the two. So the force is constant, just like this. And this is the time over which it's applied. Then if this was, say, 100 newtons, and this was 5 seconds, then the area under the graph would be 100 newtons times 5 seconds. Just vary the area of a rectangle, and that gives me 500 Newton seconds. So that would be the impulse applied in this case. If the force is not constant, it applies at 1,000 newtons and then you taper it off, then the total impulse imparted to the object would be the area under this graph. Again, impulse having units of Newton seconds, where this comes from the force and that from the time. Generally, forces are not applied all constant like this. If you were to go and push someone, for example, the force might look something like this, where you start off gently and you raise it up and then you back off again. And so the impulse in this case would be the area under this graph. Okay, so that's how we define impulse. It's the force applied over a period of time. The impulse momentum theorem, a really important concept in physics, which basically states that the impulse that you apply on an object is going to equal to the change in the momentum of the object. Okay, we're going to talk about this in a lot more detail as we move along, but first I want to break up all of these individual parts and kind of explain how we would find each one of these parts. We use the letter J for impulse, probably because I was taken and J was available. So J is equal to force times time, which is equal to change in momentum. And this equation right here is very powerful, and we'll be using it to determine final velocities, time of force applied, the quantity of force applied, etc. So let's just first do a couple of simple problems, just finding the impulse of a system. So we have a force of 250 newtons applied to an object for 5 seconds. What's the impulse? That's pretty straightforward. J is equal to F times T, and so it would be 250 newtons times 5 seconds, which gives me 1250 Newton seconds. Okay, so that would be the impulse applied in this case on some object. Second one, a ball is hit by a bat with an impulse of 30 Newton seconds and a force of 1200 newtons. How long was the ball in contact with the bat? Pretty straightforward again, since we are assuming it to be a force. It could be an average force, could be a constant force, but that's the force that we're given. So T would be J over F which would be 30 Newton seconds over 12,000, or 1200, excuse me. And this is going to be 30 divided by just 0.025 seconds, or 250 milliseconds. I'm sorry, 25 milliseconds. Okay, so that is how we find the time in a simple case like this. Next case, a force is applied over a period of time to an object shown on the graph. What is the impulse? Again, the impulse is going to be the area under this graph. If I were to find the area of this rectangle right here, it's 2 by 3, or 6 Newton seconds is the area here. And then the area for this part for a triangle is 1/2 base times height, which would be 0.5 times 2 times 2, which is just 2. So the impulse here is 2 Newton seconds. Over here is 6 Newton seconds. We add them up, and we get a total impulse of 8 Newton seconds. Okay, pretty straightforward on how we find the impulse. And remember, we're finding the impulse so that later on we can determine what will be the change in momentum of the object that I just applied this impulse to. Okay. Now we'll look and see that we said that impulse caused a change in momentum. We use delta P. Delta anything is a change in. Delta Q is change in Q. Delta T is change in T. Delta P is change in P. Change in anything is the final value minus the initial value. It gives you the change in anything at all. So in this case, what is the change in momentum for a 60 kg runner that speeds up from 4 to 9 meters per second? Now the change in momentum would be mvf minus mvi, assuming the mass isn't changing, which we could rewrite as m times vf minus vi. So that's the basic standard formula we could use to find change in momentum in any case. So then delta P would be 60 times Vf, which is 9, minus Vi, which is 4. So it'd be 60 times 5, or 300 kgms. Now this is positive, which basically means delta P increased, or the change in momentum was positive. And so whatever momentum the object might have had, it now has 300 kgms more than it did before. Okay, so this just gives you the change in momentum, not the initial, not the final, but how much the momentum changed by. Another example, a car weighing 11,760 newtons is moving at 15 meters per second, acted upon by brakes. Brakes apply a force of 650 newtons until the car slows down to a speed of 5 meters per second. What is the change in the car's momentum? Well, the change in momentum again is mvf minus vi. Now in our case we weren't given the m, but we were given the weight of the object. If you recall, weight is the mass of the object times the gravitational acceleration. So our mass, of course, would be weight divided by the gravitational acceleration. And g, for most of our purposes, will be 9.8 meters per second square. And so in our case, it would be 11,760 divided by 9.8, which gives me 1,200 kg. Okay, so now I can continue. Delta P would equal to 1,200 times the final velocity, which is 5, minus the initial velocity, which is 15, which gives me 1,200 times negative 10, or negative 12,000 kgms. So the negative sign again showing that the momentum decreased, and our change in momentum is negative 12,000 kgms, that's how much the momentum decreased by. Next we have this 0.1 kg ball. This is where we want to be a little careful when we work through questions like this, where the direction of the object changes. In our previous cases, the object was moving in the same direction. So this ball hits the wall, it's moving at 40 meters per second, it bounces back at 30 meters per second. And we want to know what is the change in momentum of the ball. And so, again, using P, delta P is equal to mvf minus vi. We see that m is 0.1 kg, vf is negative 30 meters per second because it's coming back towards the left. The initial was 40 meters per second. So this would be 0.1 times negative 30 minus 40, which gives me 0.1 times negative 70, or negative 7 kgms. So the change in momentum of this ball was negative 7 kgms. Remember, he had positive momentum going in, negative momentum coming back. If you think about it, he had 4 kgms as he was happily moving towards the wall, and boom, next thing he knows, he has negative 3 kgms. That'd be negative 30 times 0.1. And so you could see he got robbed off 7 kgms. He had positive 4, now he has negative 3. So he lost 7 kgms of momentum. And you might say, well, what happens to this 7 kgms? I thought that momentum could never be destroyed, it's always conserved. So if the ball had plus 4, now he has negative 3. Where did that 7 kgms go? Because if he lost it, someone must have gained it. And the answer is, it's the wall. The wall will be absorbing the momentum, changing the momentum of itself. And I know that would be a very, very tiny change in anything, because the wall is connected to the earth, and so it's that whole object that will be basically absorbing the momentum and changing its own. Momentum is always, always conserved. This 7 kgms got absorbed by the wall. The wall now has that 7 kgms. Momentum is never destroyed. It simply transfers on from one point to another. So anyway, this is how we find the change in momentum. Really important that you pay attention to the signs if the directions are changing. Okay, one last final case. A blob of clay of mass 0.25 kg is thrown at a ball at 8 meters per second. The blob sticks to the wall. What is the change in momentum of the blob? And again, you could pause this video and work it out on your own. It's pretty straightforward. Delta P equals m vf minus vi. Delta P is 0.25 times vf, which is 0, minus 8. So that becomes 0.25 times negative 8, which is negative 2 kgms. So this ball had 2 kgms while he was hurtling in towards the wall, and boom, now he has 0 kgms because he's at rest. And again, as you guessed, that 2 kgms got absorbed by the wall, and momentum again is always conserved. But if we are just looking at the ball, that's all we really care about, we don't care what happens with the wall and everything else around it, then we would say that the ball lost 2 kgms, and that is its delta P. Okay, next we will look at how do we put all of this together and apply the impulse momentum theorem to solve physics questions. Until then, we'll see you next.
Thank you for watching. If you liked the video or found it helpful, please like us.